Well, we can now have a look at the performance specifications in the Z-domain. Remember that the S-domain poles are located over here. This comes from, well, the denominator of this, well, second order transfer function with complex conjugate poles to zeta omega n s plus omega n squared. So you can complete the squares. So this is s plus zeta omega n squared. This one over here is s squared plus 2 zeta omega n s plus zeta square omega n square, right? So we have added this one, so we need to subtract it. So we have omega n squared 1 minus z squared. So now it's quite easy to obtain the poles from this expression over here. You remember that the link between the Z domain and the S domain is obtained by this relation over here. So these poles in the Z domain are obtained by the exponential of Ts, and then I take the poles in the S domain, right? And if you do that, and you remember that the exponential of a plus b is the exponential of a times the exponential of b, well, this is what you obtain. So this is the poles written in polar form. So this will be R0 and this will be omega 0, right? And this is an expression that we'll use quite a lot in this course when we have to translate specifications to the Z domain. Well, notice that when zeta is equal to 1, then you have a double pole in minus omega n. So in discrete time you'll have also a double pole in, well, this will be 1 obviously, and so you'll have a double pole in the exponential of minus omega n ts, right? So when zeta is equal to 1, in the S domain you have 2 real poles. They are actually the same, so they are double, and in the Z domain you'll also have a double pole that is real. Well, remember that the gain Bode diagram of this second order process with complex conjugate poles looks like this. So this is the peak frequency, and the natural frequency lies a little bit further. So this is omega n, and if you want to pick up the dynamics accurately, you should choose omega n, the Nyquist frequency here in this case, which is pi over Ts, well, larger than the natural frequency of the system. This means that you have to take Ts smaller than pi over omega n. Okay, this is what is written over here. So what we'll do is write Ts is equal to m pi over omega n, right? And this m will be between 0 and 1. This is what we have written. So another way to see this is that omega n Ts is equal to m, alright, the m first, m pi. Okay, so what you can then do is rewrite these pole locations in the Z domain as a function of m, and as you can see, m is of course related to the sampling period and the natural frequency and the damping factor. So here you have omega n Ts so that's m, and you have omega n ts over here, so that's m also, and this is what you obtain. Another way, if we continue with this relation here, is to write omega n as m over pi ts, right? We will see later that we can use this, and this is of course omega n. Okay, so m, and that's the interpretation, is, well, the ratio of the natural frequency divided by the Nyquist frequency. Well, we have seen previously, and also in the course of state space control methods, that you can choose this method of dominant second order poles, and if you put those poles in the performance region, well, you can impose a given specification, and this specification is in terms of the rise time, the overshoot, and the settling time. We'll do something similar here in the Z domain. After sampling, the dominant second order poles are transformed to poles in the Z domain that can be written in polar form as follows. And here zeta is the damping factor, and m is the natural frequency divided by the Nyquist frequency. So this can also be written as omega n ts over pi. So for performance, we know that the constant rise time, or the rise time, is linked to the natural frequency, the overshoot is linked to the damping factor, and the settling time is linked to the real part of the pole in the S domain. So of course in the Z domain we're kind of interested in lines of constant natural frequency, so omega n here can be written as m times the natural frequency, which is m times the factor pi over ts. If ts has been selected, what you can do is fix m, this will fix the natural frequency, and then let zeta evolve from 0 to 1. So we are also interested in lines of constant overshoot, constant damping factor, so we fix zeta and we let m evolve from 0 to 1, and this will produce logarithmic spirals, and we'll see that those spirals are drawn at right angles with the lines of constant natural frequency. We know that the settling time is in the S domain related to the real part of the pole, so these are vertical lines parallel to the j omega axis, and it will transform into circles of radius that is given by this expression over here. Let us now have a look at performance specifications in the Z domain. We know that the rise time should be smaller or equal to some specified rise time. TR, the rise time, is approximately 1.8 over the natural frequency, so this imposes a constraint on the natural frequency that it has to be larger or equal to some specified natural frequency. The overshoot, well, we say that the overshoot has to be smaller or equal to some specified overshoot. This can be translated on a constraint, in a constraint on the damping factor, so zeta should be larger or equal to zeta spec, right? And the settling time also should be smaller or equal to some specified settling time. Okay, the settling time is 5 over sigma is the real part of the pole in the Laplace domain, right? So this can be transformed in sigma larger than some sigma spec. So in the Laplace domain, this is how it looks like. We have the sigma spec, and the region of good performance is over here, and this will transform in the Z domain into, well, a circle, right, of radius r spec, and r spec is, well, the exponential of minus z spec times ts, right? And so we have to be inside this circle. So this means that r is smaller or equal to some specified r, right? So for the rise time, this is a curve of constant omega n in the z domain, right? So this is omega n is equal to a constant, or equivalently m, if ts is fixed, m is equal to a constant. So this type of specification, well, gives you a region that is shown here in green. What you see over here is a line of constant zeta, right? This is a logarithmic spiral. So this type of specification yields this zone over here, and this is here a zone of constant sigma or constant r, right, or constant settling time. So this kind of specification imposes a region like this. So good performance, well, this is the intersection of these three regions, and this is what you obtain. As you can see over here, everything is symmetric with respect to the real axis. This is because, of course, we work with complex conjugate poles. So very often what is done is only to show what is shown above the real axis, and this is what we'll do in the next slide. What we can do now is look at lines of constant natural frequency and constant damping. These are also called sometimes natural frequency and damping loci. So what you see here on the screen are the constant damping curves, or the constant damping loci. As you can see, this is what happens when zeta is increasing, and this is kind of what you expect, because when zeta is tending to 1, you expect poles on the real axis. Well, these are lines here with constant natural frequency. Remember that m is omega n, the natural frequency, divided by the Nyquist frequency, and we will see later in Matlab that these curves are not expressed in m, but are expressed directly in the natural frequency. So the natural frequency is m times the Nyquist frequency, so m times pi over ts. You can see that these lines here are at a right angle with the logarithmic spirals. This type of diagram can be used for pole placement in the Z domain. Well, you can generate the same kind of diagram in Matlab. You first have to create a figure, and then using the command zgrid you obtain a diagram that you can use for pole placement in the Z domain. If you want to have the unit circle appear as a circle, you should also use axis square. So you can see here the lines of constant damping, and here it's the damping associated with 0.9, and you have the lines here of constant natural frequency, right? And here the natural frequency is really written in terms of omega n, so it's m times pi over ts. So the t that you see here is the sampling period. We can now have a look at the sampled pole location when ts is decreasing. So this is the sampled pole location, and we replace this omega n ts by m pi, so you obtain this expression over here. So when ts is decreasing, then m is decreasing. Remember that m is really the natural frequency divided by the Nyquist frequency. So you can rewrite these poles here in polar form, and you can see that when ts is tending to 0, r0 here, the radius in, or the distance to the origin in this polar form, tends to 1. This can be observed from this expression over here. And here the discrete frequency that is given over here, right? Well, this is the equivalent frequency to the damped frequency, but in discrete time. So it's the discrete damped frequency. We could write it like this. Well, you can see that when ts, the sampling period, decreases, this damped discrete frequency tends to 0. Okay, another way to see this is that this frequency here over here, discrete natural frequency, which is omega n, the natural frequency times ts, well, it also tends to 0. So you can see that the two poles here track the constant damping curve. Okay, they follow the curve associated with zeta is constant, and they move to real poles located in 1. Okay, radius 1, discrete frequency tends to 0, so the two poles indeed move to real poles located in 1. Well, to see why this is the case, we simply have to look at one period. Okay, so here we have the natural frequency, so the associated period is this expression over here, and we see that as a function of ts we take more or less samples in this period. Okay, remember that m pi is equal to omega n ts. This one here is 2 pi over tn times ts. We can cancel out the pi, so ts here is m tn over 2. So for instance, if you have m is equal to 1, then you have 2 samples in one period. If you would take, for instance, m is equal to 0.1, then you can see over here that you have 20 samples per period. As you can see over here in the Z domain, everything is normalized to the sampling period, so you see everything in samples, whereas in the S domain you see everything in time, right? And this explains why when ts is tending to a small number, well, the natural frequency goes down. We see everything in terms of samples, and we'll illustrate this in an example right now. Well, let us take an example and let us consider the second order system that, for instance, we might have obtained by looking at specifications in the continuous time case. And in this case, omega n is 5 radians per second and zeta is equal to 0.6, right? So you can have a look at the, well, poles in continuous time, and if you compute the formulas, you'll see that the poles are located in -3 plus minus j times 4. So we can also have a look at the corresponding sampled poles. Okay, remember that m is equal to omega n times ts over pi. So omega n is 5 over here. So we can compute the discrete poles. Zeta is equal to 0.6, and knowing ts, well, you know m and you can find the poles. So this corresponds to m is equal to more or less 0.4. This is m is equal to more or less 0.16. M is more or less 0.04, and this is m more or less 0.0016, right? And you can see indeed that the poles move to a pole, a double pole in z is equal to 1, and we can now illustrate this on a diagram. So here you can observe this visually. This is the sample pole location where ts is decreasing. Okay, this corresponds to a ts of 0.25, so an m of approximately 0.4. So that's, you can see over here, and indeed you're on the curve that corresponds to zeta is equal to 0.6. And as you can see, well, when ts decreases, the sample pole locations moves on this logarithmic spiral corresponding to zeta is equal to 0.6, and it moves towards a double pole in z is equal to 1, so a double real pole. So here you see the impulse response in black in continuous time. So this is the impulse response of the original system P of S. So what is done is to look at the discrete impulse responses, or you can see this also as the impulse responses sampled at different ts. So this corresponds to ts is equal to 0.1 second. This corresponds to ts is equal to 0.25 seconds, and we'll consider another case also with a ts that is 0.025 seconds. Here we have not shown the samples corresponding to this sampling period on the curve, otherwise you would not see the red crosses and the blue circles over here, because this ts is rather small. So this is how things look like when you represent everything with respect to time, as is done in the S domain. Well, this is how these impulse responses look like when you represent everything in terms of the samples. So here we have normalized with respect to the sampling period, and of course these impulse responses look very different because the time, the actual time that is associated to 5 samples, for example, is very different according to the sampling period. So for instance, if the sampling period is ts is equal to 0.25 seconds, then 5 samples is 1.25 seconds. If ts is equal to 0.1 second, well, then 5 samples corresponds to 0.5 second. So by representing everything in terms of samples, well, it appears, for instance, that when Ts becomes small, the associated discrete time natural frequency decreases as well. This discrete time natural frequency is the actual natural frequency of the system times Ts. Okay, and you can clearly see that when Ts is decreasing, right, you can see that the natural frequency is becoming smaller and smaller in discrete time. This is because we have represented everything in terms of samples and that we have normalized with respect to the sampling period. Well, we have seen that you can do your design in terms of the pole locations, the sample pole locations, and that you can link them with the rise time, overshoot, and settling time. Just as we have done in the S domain, we would like to study the influence of A0 in the transfer function. So what we'll do is add A0 in the transfer function and we'll adapt the gain so that we kind of keep this unit static gain, and the static gain in the Z domain is obtained by replacing Z by 1. You can see here that if you take K to be this quantity over here, well, this transfer function has a unit static gain whatever the value of Z0 over here. What we can do now is look at the step response and look at the influence of the 0 in the numerator. Here we have consider a case where the damping is 0.5, so we expect, if there is no influence of the 0, well, an overshoot of around 16%. Here m is equal to 0.1, so this means that the natural frequency is m times the Nyquist frequency, and m here is 0.1. So you can see here the different step responses with different values of the 0. So we'll draw the unit circle over here. So this is the complex plane Z, and this is the unit circle, and you can kind of see that, well, in this region over here that I'm showing you now, the influence of the 0 is rather small. This corresponds to the lines in blue, green, and pink, right? But then suddenly, when you come in the neighborhood of Z is equal to 1, the influence is larger. Okay, you can see here in light blue a 0 that is situated in 0.8, so it's a 0 inside the unit circle, and as expected, well, you have a lot of influence on the overshoot, and here you have a 0 that is outside the unit circle, and as we have seen, well, this will cause this inverse response, but it will also have an influence on the overshoot. So you can see that, well, in this region over here, well, the influence of the 0 is large, and if we would continue further down this line over here, then the influence would be rather small again. We can also have a look at the relation between the position of the 0 and the percentage overshoot. Okay, remember that we have a zeta of 0.5, so we expect around a percentage overshoot around 16 to 17%. Okay, if we look at m is equal to 0.1, remember that m is the natural frequency times Ts over pi. So this would correspond to a small Ts, and then we'll see the influence of an increasing Ts. So let us consider this case first, and as we had seen, well, if you stay outside this region here, the influence of the 0 is rather small. But if you approach 1 with the 0, then the effect on the percentage overshoot can be quite dramatic. We observe also that the effects of the 0 on the percentage overshoot increases when m is increasing, or equivalently when ts is increasing, and this you can observe over here. As expected, the major effect of the 0 z0 on the step response is to change the percentage overshoot. When the 0 is on the negative axis, it has very little influence, but its influence can be dramatic when z0 approaches z is equal to 1. So in this neighborhood, when the 0 is in the unstable region, okay, so we have so-called, between quotes, unstable 0, well, then we have, of course, an inverse response. For zeros close to z is equal to 1, but outside the unit circle, the negative peak associated to this inverse response can be very large. And when you move away from z is equal to 1 to the positive z's, right, the influence of the 0 decreases again. We've also noticed that the influence of a fixed 0 is larger the larger value of m, or the larger the value of ts, okay, because we've seen that m is omega n ts over pi. So in general, when ts is increasing, or when m is increasing, the influence of the 0 is larger. Well, in this subsection we'll look at specifications, but in the Bode diagram in terms of the loop gain transfer function. Remember that we have, well, imposed specification in terms of the sensitivity and the complementary sensitivity, and now we'll transform them into specifications on the Bode diagram of the loop gain transfer function, and we'll simply say loop gain. This will lead to loop shaping techniques that are similar to the ones that you've seen in the course of my colleague David Rouchard, Fundamentals of Control Theory. The only major difference is that you have to take into account the zero order hold mechanism, because in discrete time, well, this zero order hold mechanism introduces roughly a delay of ts over 2. If ts is very small, then sometimes you, well, can forget about the zero order hold mechanism, but in this course we are going to try to use a ts that is as large as possible, right? So the zero order hold mechanism will play a role, so we'll have to base our loop shaping on pz is equal to, well, pzoh z, so that the zero order hold mechanism is taken into account. So this is the zero order hold equivalent discrete description of the process P of S. Well, once you have this description, there are essentially two ways to do the design in discrete time, and this loop shaping design. In practice, we'll only use the second one, because the first one involves a bilinear transformation to recover a kind of continuous time type of problem, and we have skipped this in the previous sections. This is how it was done in the old days, but nowadays, of course, we can use the computer and do the design directly on the Bode diagram that is generated, for instance, by Matlab. Well, these are the specifications that we had imposed on the sensitivity function. Remember that S is 1 over 1 plus PC, and on the complementary sensitivity function, PC over 1 plus bc. Remember that s plus t is 1 over here. S and t are complex numbers if you replace z by the exponential of j omega. So s and t add to 1. This does not mean that the modulus of t plus the modulus of s add to 1. They add up to 1 as complex numbers. So these are the specifications that we had imposed in the low frequency range. So t in module approximately 1, s in module approximately 0. This we have imposed for a good reference tracking, and this we have imposed for a good disturbance rejection and insensitivity to variations in the process. And this needed a module of PC that is high, so a high loop gain in the low frequency ranges. So this means an integrator in the loop is a good thing. In the high frequency range above the bandwidth frequency, we had imposed that the module of t is as small as possible, and this means that you take a low loop gain so that the module of p, c, is small in the frequencies above the bandwidth frequency, and this will ensure that, well, you have insensitivity to unmodeled dynamics and insensitivity to measurement noise. Well, we can now look at the specifications on the Bode diagram of the loop gain. Remember that in the low frequencies the loop gain must have a high gain, and at the high frequencies the loop gain must be small. So this loop gain must be small above the bandwidth frequency. Of course, there is a transition between low and high frequencies, and this is the region that you see over here, and typically this zone ranges over a frequency range of more than a decade. It is in this zone that the stability margins and therefore robustness is going to be imposed. Well, this loop gain goes through a gain of 1 at some frequency, which is the gain crossover frequency. So a gain of 1 corresponds to 0 dB, and it is at that frequency that you impose the phase margin. This is why the slope that you have here in this zone, well, cannot be too small. Well, the minimum slope, but that's the very minimum, is minus 40 dB per decade. If you go lower, there is no phase margin. It will actually become negative, so that's not the way to go. And well, generally what is advocated is that in this zone the slope should be around minus 20 dB per decade. Well, this point also will be linked to the bandwidth and to the time constants in closed loop. In the low frequency range, we wanted the gain of PC as high as possible, so we're pushing here, and this is because we want a good tracking performance, and we want insensitivity to process variations, and we want to be able to reject low frequency output disturbances. In the high frequencies, we want a loop gain PC in module as small as possible. So this means that we're pushing here downwards in this gain Bode diagram of the loop gain, and this is because we want to be insensitive to measurement noise and insensitive to unmodeled process dynamics. If you combine the last 3 slides, this is what you obtain. We will have the opportunity to apply this methodology in the section that is devoted to loop shaping. We will now make a little summary of all this and have a look on how you can determine the crossover frequency and the phase margin from the specifications on the closed loop system in terms of, well, settling time or closed loop time constant, and in terms of the desired overshoot. So at low frequencies, the loop gain must be large. This is to have a good tracking, good rejection of low frequency disturbances, and to be insensitive to variations in the process. So what you have to do is to have a steep slope in the gain curve at the low frequencies, and this can be typically ensured, for instance, by putting an integrator in the loop transfer function, so either in the process if it is there or in the controller, and there you have the choice to put it yourself. At the high frequencies, this loop gain in module must be small, and this is in order to avoid injecting too much measurement noise, in order to avoid amplifying the measurement noise, and also to guarantee a certain insensitivity to high frequency unmodeled dynamics. In between this low frequency region and this high frequency region, you have a transition, and this transition must be as smooth as possible over a sufficiently large frequency range, so a decade or even slightly more. In this frequency range, the loop gain slope should not be less than -40 dB per decade. This is because otherwise the phase shift is too large, and in general a slope of -20 dB per decade is advocated, and we'll show this next. Such a transition ensures, well, good stability margins, and we will show next that the phase margin, the damping ratio, which is itself linked to the overshoot, and the slope of the curve, they are all linked. And also this kind of smooth transition links the crossover frequency omega c to the natural frequency of the system, so it links it also to the closed loop bandwidth, right, and also to the dominant or main closed loop time constant. This is what we'll show next. So what we want to do is to impose a second order type response. In the coarse state space control methods, we do this by a pole placement. We place the two dominant second order poles. Here we'll do the same thing, but in the frequency domain in a Bode diagram, working on the loop gain. Remember that we receive specifications in terms of overshoot, okay, and the overshoot can be linked to the damping ratio using this formula. For instance, if you have an overshoot of, or desired overshoot of 16-17%, well, you know that this corresponds to a zeta of roughly 0.5. Apart from this specification on the overshoot, you probably have a specification on the closed loop dominant second order poles, okay, or on the closed loop time constant, okay, here it is, and it is linked to the real part of the closed loop dominant second order poles by this formula over here. So instead of having the specification in terms of the closed loop time constant, you might have the specifications in terms of the closed loop settling time, but then of course the relation becomes like this. It's 5 divided by zeta omega n. This is this sigma that we had defined previously. But anyway, from the specifications you can determine the damping ratio and the natural frequency, and now we have to kind of link this to our design in the Bode diagram of the loop gain. So we have to kind of transfer this to a crossover frequency omega c and a phase margin Vm. Well, we want to impose this closed loop transfer function, right? Remember that the complementary sensitivity function is linked to the loop gain Pc by the relation 1 plus Pc, so L over 1 plus L, right? So now from this closed loop transfer function we would like to construct L. If you look at it, well, L is constructed from T by inverting this relation over here, this one over here, and this will produce T over 1 minus T. Okay, so L of S is T over 1 minus T so we have to put this under the same denominator, and what we'll have is omega n square and then s square plus 2 zeta omega n s plus omega n square minus omega n square. These ones will simplify, so we have an L of S that should look like omega n square S times S plus 2 zeta omega n, like this. So imposing this closed loop transfer function, well, is equivalent to imposing this loop gain. Well, looking at the specifications that we had imposed on the loop gain, remember, so in the low frequencies a high value of the loop gain module and a high slope, and then at the, well, in the transition zone something that is more or less here a decade, and then, well, a loop gain that has a high roll-off and a low value of the gain in the high frequency ranges. And, well, imposing an L of S that, well, kind of is a consequence of the closed loop transfer function that we have imposed here of Ls is equal to omega n square S plus 2 sigma omega n, is kind of reasonable as long as this region here around the crossover frequency is smooth with a slope that is around 20 dB per decade, and that this occurs, and that this transition occurs over a sufficiently large frequency range, typically a decade or more than a decade. This is equivalent to saying that, well, if you work with dominant second order poles, as we have done, for instance, in the course of state space, well, the dominant second order poles are not too close to additional poles and zeros that you might have in your design. Okay, so imposing this L will be consistent with the specification that we have imposed on the loop gain, as long as this transition zone around the crossover frequency is sufficiently large with a smooth transition and a slope, well, that is in the neighborhood of minus 20 dB per decade. So what we'll do right now is impose this second order type closed loop response. We know that this is equivalent to imposing a loop gain that is like so. we know that the specifications will produce a certain omega n and a zeta. So the question is, in our frequency design, how can we find omega c and how can we obtain the phase margin, right? So what we'll do, we'll study this loop gain, we'll fix omega n, right? It is fixed, and we'll see how the phase margin, okay, so this is Vm, the crossover frequency omega c, and the slope at the crossover frequency evolve with damping ratio, and we'll obtain curves, a table that will allow you to link the natural frequency and the damping ratio to the crossover frequency and the phase margin. These specifications, this method is valid in continuous time in the Laplace domain, but you can also use it for discrete time design as long as you work with a loop gain that is constructed from a model that takes into account the zero order Hall mechanism, right? So when I write P of z here, I assume that this P of z is the zero order Hall equivalent, discrete time equivalent of the continuous time process. Well, we have imposed a second order type response, and we have seen that this is equivalent to imposing a loop gain like so. So what we can now do is look at the features, for instance the crossover frequency, the phase margin and the slope. Well, to compute the crossover frequency you have to find the omega, the frequency, such that, well, the modulus of L in j omega is equal to 1, and this is what you obtain. So what is interesting here is that you can plot omega c over omega n as a function of zeta. Remember, from your specifications you will have omega n and you will have zeta, so this will allow you to obtain omega c, right? So you can also compute the phase margin. You look at the phase shift at the crossover frequency and then you look for how much margin you have, and this will result in this quantity over here. This phase margin is of course dependent on the crossover frequency. What is neat here is that it depends again on omega c over omega n, which is this square root over here that you see. So you can inject that in here and you can see that the phase margin will only depend on the damping ratio. So what you can do again is plot the phase margin as a function of zeta. Finally, you can compute the slope, and here's the formula. You can kind of see that this formula makes sense. For that we'll take some special cases. The first special case is zeta is equal to 0. If you inject zeta is equal to 0 over here, you have a double integrator and you would expect a slope of minus 40 dB per decade. If you do so, zeta is equal to 0, these terms over here will disappear, the omega to the power 4 will simplify and you'll end up with minus 40 dB per decade, right? So now we can have a look at zeta different from 0, and we can look at small frequencies and large frequencies. When I say small, it's smaller than, much smaller than the natural frequency, and large, it's much larger than the natural frequency. So let us start with frequencies that are much smaller than the natural frequency. Well, this one will behave here as an integrator, so we would expect a slope of minus 20 dB per decade. And indeed, if we put a small value of omega in here, well, what will happen is that these omegas to the power 4 will become really small, and so you can cross out these powers over here, and you have exactly the same thing at the numerator and denominator, so you find minus 20 dBs per decade. If omega is much larger than omega n, then these terms will be larger than the terms over here, so you can cross out these two. The omega 4 will simplify, and you'll end up with minus 40 dB per decade. So this formula of the slope at any frequency makes sense. Of course, we are interested in the slope at the frequency omega is equal to the crossover frequency. What we can do now is look at all those features as a function of zeta. So you can see here that we loop over zeta, going from 0 to 1 by steps of 0.05. So we look at the Bode diagram of the loop gain, and this is the loop gain that we impose, right? And then we compute the phase margin, the overshoot, the crossover frequency, and the slope. We do this for a value of the natural frequency, but you will see in the next slide that everything is represented as a normalized quantity. So for instance, we'll represent the normalized crossover frequency by dividing by this omega n, and we had already done so for the phase margin, and you had seen that it only depended on zeta. You can see here that we plot a number of things as a function of zeta. So we plot, for instance, the phase margin, the overshoot, the normalized crossover frequency. You can see here that we normalize everything with respect to the natural frequency. So here in these four plots, everything will become independent of the natural frequency that we have chosen. The relevant quantity is omega c over omega n, and here we plot the slope at the crossover frequency as a function of zeta. So we can have a look at the Bode diagram of the loop gain that we have imposed. So omega n squared s times s plus 2 zeta omega n. So here we have considered several zeta, and zeta is increasing in this direction. This one corresponds to zeta is equal to 0. In this case you have a double integrator, and this is consistent, minus 40 dBs per decade everywhere, a phase shift of minus 180 degrees, so a phase margin of 0. This is what happens when zeta is damping ratio is increasing, and you can see now that in the low frequencies we have indeed this minus 20 dBs per decade, and in the high frequencies minus 40 dBs per decade, and this had been announced previously. You can see here that the crossover frequency is decreasing. The formula says that the omega c divided by omega n is the square root of the square root of 1 plus 4 times zeta to the power 4 minus 2 times zeta to the power 2, right? If you put zeta is equal to 0 in here, you can see that this will produce a 1. So we have omega c is equal to omega n, and this is indeed the case. In this case here omega n was 10 radians per second, and well, for zeta is equal to 0, omega c corresponds to omega n. Let us take the other value, and the maximum value here, zeta is equal to 1, and then you can see here that omega c is the square root of the square root of 5 minus 2 times omega n, and this is approximately 0.48 times omega n, and this looks about right. So up, yes, this is okay, right? So you can see here clearly that when the damping ratio is increasing, the ratio omega c over omega n is, well, decreasing from a value of 1 to approximately 0.48. You can see also, and this is here zeta increasing, that the phase shift in the Bode diagram of L is decreasing. So this means that the phase margin is increasing. So this is the plot where you show phase margin in degrees as a function of zeta. When zeta is equal to 0, we had seen that the phase margin was indeed 0, and it increases to a value, well, that is in between 70 and 80 degrees phase margin when zeta tends to 1. Here we see a plot of the overshoot with respect to zeta. Of course, a value of zeta is equal to 0 corresponds to 100% overshoot, and zeta is equal to 1 to 0% overshoot. But you can find here the values, for instance, that correspond to 0.5, and if you have a look, as you can see, this corresponds to this 16-17% overshoot, a value that you know very well. This is the normalized crossover frequency, omega c over omega n, as a function of zeta. As we had seen in the Bode diagram of L, when zeta is 0, omega c and omega n correspond, but when zeta increases, well, the ratio decreases to a value of approximately 0.48. Well, this is the slope at the crossover frequency, and it's a function of zeta, and you can see here that really this slope in this transition region from low frequencies to high frequencies should definitely be higher than minus 40 dB per decade, and really in what ranges of zeta that you use in a design, you can see here that imposing a slope around minus 20 dB per decade is certainly reasonable. Well, as you can see, you can put everything in a table, and a same kind of table was obtained in the course of my colleague David Rouchard, Fundamentals of Control Theory. So how can you use this table? Well, you know from the specifications in times of overshoot, settling time, or closed loop time constant, well, you obtain a value of zeta and a value of the natural frequency. Based on this value of zeta, right, well, you can have a look in one of these rows over here, and what you then obtain is the phase margin, right, and the normalized crossover frequency. Since you have the natural frequency, you also obtain the crossover frequency, and now you have information that is relevant to you to do loop shaping in a Bode diagram of the loop gain. We'll explore that in the section that is devoted to loop shaping. So what have we learned so far? Well, we have learned that the phase margin, the overshoot, and the slope at the crossover frequency, but also that the normalized crossover frequency depend on the damping ratio. So once you have the damping ratio, you can obtain the crossover frequency and the phase margin. In practice, you can impose a slope of around 20 dBs at omega is equal to omega c, so at the crossover frequency. So the assumption is that the closed loop is a second order system with dominant complex conjugate poles, and equivalently that the gain, the loop gain, behaves as this transfer function. In reality, the loop gain will deviate from this, but if this transition region is sufficiently wide, more than a decade, and if, well, the transition is smooth and that you impose this slope of around minus 20 dB per decade, well, the closed loop behavior will not deviate much from a second order behavior with dominant complex conjugate poles. Well, in practice, what we'll do is have specifications in terms of the overshoot very often, but sometimes also directly in terms of the phase margin, and we'll receive a desired closed loop time constant. Sometimes instead of the desired closed loop time constant, we'll say that we have a desired settling time TS. Okay, so instead of having this relation, well, you have that TS is, well, 5 over zeta omega n. Okay, because the settling time is roughly 5 times the closed loop time constant. So when you have those specifications, what you obtain is zeta and omega n, and we have just seen how you can transform this in Vm and the crossover frequency so that you can start your loop shaping procedure. Very important is that the previous analysis is valid for a system without delay. In the presence of a delay, well, things are a bit more difficult, okay? And if this delay takes substantial, well, values with respect to the main time constant, it becomes more and more difficult. What you can do as a rule of thumb is modify this relation to the one that you have over here. So in combination with this relation, and given an overshoot and a phase margin, you can again determine zeta and omega. This will work for, well, values of theta that are not too large with respect to the main time constant of the system. Well, we'll see here that in discrete time you can still use the root locus. In this last subsection, the pace will be a little bit faster because this is material that you've seen in last year's course, Fundamentals of Control Theory. Knowing the locations of the poles and the zeros is important. For instance, the location of the poles will tell you if the system is stable or not. And poles and zeros, well, they affect the transient response. A good example of that is a zero that is outside the unit circle will impose an inverse response during the transient. An important property of the control system is the variations of the pole locations as the controller gain changes, and the root locus is a graphical way of quantifying these variations in the pole locations. The root locus, by definition, okay, it's the roots of the denominator. Well, the root locus does not say anything about the zeros of the system. The good news is that the construction of the root locus is identical in continuous time and discrete time. There is even better news, because you remember that, well, in continuous time the root locus can only handle transfer functions that are irrational in S, and these methods are unsuited to, well, deal with delays because there is the appearance of the exponential of minus theta s. There is no such problem in discrete time, as delays are handled in a polynomial way. You can use the same rules as the ones that you used last year for discrete time systems, and also the conditions on the modulus and the argument for a pole to be a pole of the closed loop system are identical. Although it is easier to use the computer to draw the root locus, it's always a good idea to know these rules for sketching the root locus, because they give you an insight as to how the root locus can be shaped using a given controller structure, PI, PID, lead lag compensator, and so on. Of course, the interpretation of the root locus is different in the S and the Z domain, because a different grid is used to translate performance specifications into pole specifications. Remember that we have seen this Z grid previously in the course. So let us take an example of a continuous time system and then its zero order hold equivalent discrete time description. So this system is P is 1 over S 10S plus 1. It's the process that we'll consider very often later on in the course, and what we do is discretize here with a TS is equal to 1, and we obtain PZOH of Z, right? So we'll see when we consider the root locus of the original continuous time system and then the root locus of the discrete system that we draw different, well, conclusions. We will see here that there are, well, 2 zeros at infinity, but after discretization here we'll have 2 poles and 1 zero, one finite zero, and there of course is another zero at infinity. So you see here that the situation is already different. We will see here that as far as the critical gain is concerned, well, the critical gain is infinite, but here after discretization we have to take into account the zero order hold mechanism, and we will see that the critical gain is no longer infinite. Well, in continuous time we have to use this S grid that you have used last year. Remember that the root locus with a gain 0 starts from the poles, and the poles are in 0 and minus 1 over 10, right? They move towards one another and then they go to the zeros at infinity. So we have here, as n is equal to 2 branches, but you can see here that the critical gain is infinite in this case. So in discrete time we have to use this Z grid that we have introduced before. So here is the finite zero, there is another one at minus infinity, so there is a pole at 1, and there is a pole at the exponential of minus ts over t, right? So here this corresponds to the exponential of minus 1 over 10. So the root locus starts at the 2 poles, then the root locus, well, moves towards the zeros like this. Here the 2 branches will encounter somewhere over here, and then one branch will go this way and the other one will go this way. What is important to see here is that the closed loop poles will leave the unit circle. So if you use a controller with a gain that is above the critical gain, right, so a proportional controller, you will see that the system will become unstable. This is clearly different to the situation that we had in continuous time, where we had a infinite critical gain, and this is of course because of this zero order hold mechanism that introduces a delay of roughly ts over 2. So we'll go over the definition of the root locus. We take the loop gain and we factor out the key parameter that we want to vary when we look at the root locus, and in general it will be the controller gain. So we write the loop gain as kc times a transfer function, and this transfer function is constructed from 2 polynomials bl and al. Without loss of generality, you can take this one monic. Okay, if you have a parameter over here that is not 1, assuming that it's non-zero, of course, well, you can divide by this parameter to make sure that this one becomes monic, right? This one has degree n, this one has degree m. Okay, we'll assume that the loop gain is strictly proper. This is not a restriction because in practice the process will itself be strictly proper. If it's not, well, it would mean that you have a direct feed through. Okay, and in a practical system this is not to be expected. What you can then do is factor numerator and denominator and write this loop gain as follows. Since AL is monic, you have a 1 over here, and BL is not monic, so you have to take the B0 over here, which we assume, of course, to be different from 0. So remember that all closed loop transfer functions have 1 plus BC or 1 plus L in the denominator. This is something that we have seen previously when we've considered all the transfer functions, for instance, what we have considered internal stability. By definition, the root locus, well, looks at all the zeros of this denominator when the controller gain moves from 0 to infinity. This one is here KC, BL over AL. So if you inject that, looking at 1 plus LZ is equal to 0 is equivalent to looking at this equation here when KC is in the range 0 to infinity. So imposing this is equivalent to imposing that the loop gain is -1. Okay, this is the loop gain. So we call this the root locus, but you know from last year's course that we can call this in French lieu des pôles, lieu des racines, ou lieu des vents. The condition that we had, that the loop gain is -1, can be written in terms of the argument and the module as follows. Right? So this can be further detailed if you remember that L of Z is KC B0 and then Z minus Z1 up to Z minus Zm over Z minus P1 up to Z minus Pn. So if you take this and compute what it will give when L is described as follows, this is what you obtain. Okay, and these are the conditions that you've seen in last year's course, Fundamentals of Control Theory, and these two conditions are the conditions for a point in Z now, a point Z in the Z plane, to be part of the root locus of LZ. As you can see, the first condition is independent of KC. So this condition is used to shape the locus in order to make sure that this locus passes through pole locations that are determined from the performance specifications. Once you have ensured that your root locus passes through these pole locations, you have to choose KC in such a way that the closed loop poles correspond to the desired pole locations. In this equation, well, if B0 is positive, well, this argument of B0 becomes 0. So if B0 is 0, you can leave out this term over here. Well, let us have a look at the properties of this root locus. It has, well, n branches. N is the degree of AL, so the denominator in the loop gain, and the root locus is of course symmetric with respect to the real axis. We had seen that this condition 1 plus L Z is equal to 0 is equivalent to ALZ plus KC BLZ is equal to 0. This is the numerator of L and this is the denominator. So when KC is equal to 0, well, the equation that you have to solve is ALZ is equal to 0, right? So you can see that the root locus will originate from the poles of LZ is equal to 0 when KC is equal to 0. And this is KC is equal to 0. So when KC tends to infinity, well, this will be equivalent to solving BLZ is equal to 0. So you can kind of see that M of the n branches will lead to the zeros of L of Z, so to the zeros of this polynomial BL. The other n minus m branches will go to the zeros at infinity, so we'll have asymptotes when Kc tends to infinity, and these asymptotes will make angles that are this value if b0 is positive and this value if b0 is negative. Well, we have just seen that n minus m of the branches will go to the zeros at infinity and make asymptotes. Well, these asymptotes will merge on the real axis on a point that is given by this equation. So if b0 is positive, a point on the real axis is part of the root locus if the total number of poles and zeros on the right of that point is odd. So for instance, if this is the real axis and you have here a pole, here a pole, and here a zero, for instance, well, then you know that over here this point will be part of the root locus, and this one will also be part of the root locus, because over here at the right, well, you have 3 poles and zeros, so the condition is satisfied. Here to the right of that point you have 1 pole, so the condition is satisfied as well. If you have b0 negative, well, you have to replace odd by even in the previous sentence. Well, sometimes there are also breakaway points and break-in points. You've seen this in the, well, 2 root loci that we have seen previously on the real axis. Well, the points at which you have the breakaway or the break-in can be computed by solving this equation here, and here the derivative is taken with respect to z. Let us take an example. The example is over here, and have a look at the root locus. So this is the loop gain that we are considering. So we have here no zeros, right, and 4 poles. You have 3 poles at the origin and 1 pole at point 9. So you can kind of see here that on the real axis the root locus will be located in between 0 and point 9. We have m is equal to 0, n is equal to 4, so there will be n minus m, so 4 asymptotes. We can see that these asymptotes will merge on the real axis. There are no zeros, so you just have to sum the poles and divide by 4. So these asymptotes should merge at 0.9 over 4. Let us have a look at the root locus. We have 3 poles at 0 and 1 pole at 0.9. So a point over here is indeed part of the root locus, because to the right there is an odd number of poles of zeros. In this case it's a pole. Well, you can kind of see that the root locus will start from the poles. So here it will evolve like this, here it will evolve like this, and the third pole will evolve like this. Okay, so here you have a breakaway point, and you can see that there will be 4 branches, so 4 asymptotes, and you can see here that the asymptotes will merge on the real axis on a point that is, well, 0.9 divided by 4. Well, here b0 is positive, so the angles of the 4 asymptotes is 2k plus 1 pi over 4. So this will lead to these angles. So we can also compute the breakaway points, and in this case we have to solve ALZ, BLZ, take the derivative, minus BLZ, and then ALZ, and take the derivative and find the roots of that. This first term will not give a contribution because the numerator is constant. So this is the equation. We have to take the derivative. This is what you obtain, and if you go through the calculations, you'll find a breakaway point in z is equal to 0 and 1 in 2.7 divided by 4. Well, let us check that. You can see here that the angles that the asymptotes make are indeed pi over 4, 3 pi over 4, and etc. When we look at the breakaway points, you can see indeed that there is one in 0 and another one over here, and that's in 2.7 divided by 4.